All right, everyone. Thanks for coming out again on a Saturday afternoon. Today we're talking about sample-based quantum diagonalization and variational quantum eigensolvers along with quantum chemistry. Now, it's okay if chemistry is not your primary pursuit. Both of these are very useful for a variety of different other tasks. But sample-based quantum diagonalization is one of the more interesting algorithms just with um, how well it is leveraging the NISQ capabilities. It's truly embodying that aspect of use the quantum aspect for the part that it does best while using the hybrid with classical computing in order to, leverage the current capabilities of quantum computers. So these tools have all been developed originally with the idea of finding molecular ground states. So finding the ground state of, or the electron energy of a nitrogen molecule, for example. Um, However, it's important to understand that the Hamiltonian of this atom is a representation that we can apply to quantum computers, but we can also apply many other types of problems, whether that's finance or material science. It's all very new, and people are still finding new ways all the times to apply these. Um, there are two basic techniques that we're going to discuss here. One is VQE, which is a variational quantum eigensolvers. It is an iterative update, guess and improve the energy. It's able to garner some really interesting results, but it suffers a lot from the amount of noise that it takes to run a circuit that deep. Then we have SQD, and it's a cousin SKQD, which we'll talk about a little bit, which are really good about just sampling the noisy data quickly and then cleaning and solving those problems classically. So instead of trying to do all the computation on the quantum circuit, we try to, jump in and sample the state of the system, and then we're solving that classically. The reason that quantum computing has emerged as being so successful at these kinds of systems is it's why quantum computers were proposed by Richard Feynman in the first place. Quite early on, we saw that it was really difficult to classically simulate quantum systems. These systems that have these behaviors where, they have principles of spin and entanglement and things like that. So it makes sense for us to use quantum computers to model quantum systems. But we don't have to just use this for quantum chemistry. SQD is very noise resilient. We use the quantum circuit to sample the system, and then we're cleaning that up and processing that classically. SQD works for Hamiltonians, that is these energy states of these systems that are large and sparse. A sparse matrix is one that's mostly filled with zeros. Many systems that we actually work with, are these sparse systems. Some of the key non-chemistry domains that have been applied are optimization problems. Think things like the traveling salesman problem. That is that, Amazon routing. Hey, how should we visit all these stops that are necessary? There's all kinds of optimization problems where we have, functionally infinite number of ways to combine these things, but how is it that we're going to find the optimal way? Material science is that we can simulate these lattices of how these things are connected. Other physics simulations, process adaptation. So there's a lot of things that we can represent in a way where it's useful to gather the eigenstate information of that system. It's a graph theory there's a lot of stuff there as well. And graph theory is what I worked on in my master's thesis. But with graph theory, oftentimes we can analyze the spectra of the graph, that is its eigenstates, eigenvectors, and eigenvalues, and deduce a lot of information from that. But calculating the spectra or even approximating the spectra is prohibitively expensive. So by being able to use this VQE and SQD to approximate that and quickly be able to solve problems like that's useful for just so many different kinds of problems. So it's been applied with finance and portfolio optimization, where we map the system by binary constraints, and we adapt it to SQD to find the lowest energy states. That is, the states that have the greatest reward with the least cost. With machine learning, there are quantum kernel methods, very similar to your classical kernel methods, where we estimate the kernel overlap. But with high dimensional kernels, even that can become costly, and SQD can help refine those noisy samples. And then with high energy physics, I don't know a lot about this, but at the same time, these same kinds of states occur there. Then also there's applications in cryptography, and then AI with trying to optimize sparse neural nets. So we're going to stick with the chemistry example here. One, it's the one that there's the most details on, and it's the one the notebooks that I've provided follow. But we have these electrons that are dancing around a nucleus of an atom. They have their specific properties, that no two of them can be in the same spot, and that no two in the same orbital can have the same spin. So you have these pairs of spin this way, spin that way orbitals. But with calculating the ground state energies of this, the math explodes. Even with the best supercomputers today, anything beyond a very, very small molecule is just prohibitively expensive to do any calculations on. However, we're able to use qubits to mimic these electron orbitals directly. So we take a definition of a molecule, and then we compute these energy terms. These are defined methods of doing that. There are things called like Hartree-Fock that are used to approximate these terms. We then map those energies to our quantum energy operator, and then we iterate with that with those, optimization algorithms to find the lowest energy state. So whereas with the classical methods, it's more like manually counting beans and testing every configuration. With quantum, it's more like we are shaking the box so the heaviest elements drop to the bottom. The SQD workflow. And I understand that this seems very abstract and difficult and complex. The notebooks take a little time to parse, but also at the same time, people in the Qiskit add-on environment have done a lot to abstract away elements of this to where it's a more straightforward workflow. It handles these big, noisy Hamiltonian states, these large matrices that represent the energy states of these systems. So the first step is to prepare an ansatz. And ansatz is a term we're going to hear about more and more moving forward. An ansatz is simply a quantum circuit with tunable parameters. We've talked about that a little bit in the previous session. So we prepare the ansatz on the quantum device. We then sample electron configurations. All right, we clean these samples. We pass this through our sample subspace, through our quantum circuit. And then we classically clean and refine those results. So it's one of those things where it's like quantum is selecting the puzzle pieces for the classical solver to put back together, but it's not 10,000 puzzle pieces, it's 100. It's very noise tolerant. So here's a little chart I wrote up. So you prepare the circuit. We build a quantum circuit just like we have. You'll see this LUCJ. That's just a method of preparing the circuit. It's a unitary circuit, the Jaslow circuit, using those Hartree-Fock states, these energy states that we have defined for these atoms. We then execute that on our quantum hardware or simulator and collect these noisy bit string samples. Okay, and then we estimate what these energy states mean for that particular molecule. So we'll sample from that and we'll flip any bits that violate what they should be. We'll try to update that, and then we'll reproject that into the Hamiltonian space and do it again. And so what we do is we're building on our simulation of this molecule, moving towards the most self-consistent state of that molecule. The Jaslow ansatz, the local UCJ, is a sparse way of encoding this information into our quantum circuit. We limit it to pairs to match the topology of the actual device that we are working on. So we start from that energy and we provide some rotations and then optimize. And so what we literally do is, if we're trying to simulate an atom that has 15 orbitals, 15 matched pairs of electrons, that is, I'm not any chemist here, I'm very sorry. But we map these to the exact device such that they are paired at every 5 elements like this. And what that does for us is that it reduces the amount of swap operations we have to do on this circuit. So this is how it's actually laid out on the device, with each one of these corresponding to a qubit. And that keeps our circuit short, so we have to deal with much less noise whenever we're running our circuit. If we just naively threw this at a quantum circuit, the circuit could be hundreds and hundreds of gates deep, and we'd have to apply significant error mitigation or cancellation to try to work with it. But this method allows us to take a circuit that's 35 qubits wide and to map it onto an actual device in such a way that our circuit doesn't become hundreds of qubits or hundreds of gates deep. And it's the self-consistent configuration. We know these things about how these electron orbitals are going to behave, that these electrons are paired with one spin in one direction and one in another. They can't simultaneously be in 2 orbitals at the same time. They have that quantum constraint on them. And so we estimate the orbital occupancies from raw samples, we check for violations, and we probabilistically just flip bits that violate. Okay, so we probabilistically flip those bits, and then we pass that back through our quantum circuit to refine our estimation of the ground state energy of these molecules until we reach some tolerance, or whenever they converge. And so we just take, we've already covered this. The big thing here, though, is that zigzag layout, that we're matching the architecture. And the preset pass managers and the transpilation steps that we've talked about earlier, those methods to reduce gate counts and make more efficient layouts, are great and wonderful. But a lot of times for these more complicated circuits and things, a human can still do better at manually setting the layout of which qubit should be which other one. That way we reduce the complexity of that circuit and have to take less steps to manage noise. Another aspect about this is that many of the toy circuits that we play on, we see shot counts in the neighborhood of 1,000 or 2,000. But to get a smooth enough gradient for these to operate on, we typically run around 100,000 shots on like the Heron class devices, which are the latest IBM devices that we have access to. Now, the variational quantum eigensolver, this has been around longer than SQD, but with this one, whereas we're taking those quick snapshots with SQD, then classically solving it, we're iterating more with the variational quantum eigensolver, more on the circuit, and so it suffers more from noise. One of the aspects of it that are useful, though, is that it's a little bit more flexible. We're not sitting there manually specifying the qubit positions and setting it up to exactly match a molecule. It's a little bit more adaptable. I have students in my class using variational quantum eigensolvers to solve a variety of problems, from finance optimization to mapping the folding of enzymes and things like that. It's a little less fragile in how it's set up, but it's very sensitive to the noise. It can still benefit from the same behaviors that we apply to SQD, but that's not been the way it's generally been laid out. So in general, if we're trying to decide the handoff here, VQE versus SQD, VQE is iterative and very good for small systems and optimization. If you have a quantum circuit or a problem that you can express on a handful of qubits, 5 to 10 or 15 qubits, VQE can rapidly iterate. We don't have the issues with the noise. We do these quantum measures with that classical loop. As the problems start growing in complexity, we have to be much more aware of the limitations of the NISQ hardware. So SQD is allowing us to do a quantum run and then just classically refine that and to test those energy states. Another issue that VQE can run into is a common problem in quantum computing is called the barren plateau. What that has to deal with is that for every qubit, we are representing our information in a space that is 2 to the number of qubits large. So for a 10 qubit system, we're operating in a 1024 dimensional space. And the cursor dimensionality applies to quantum systems just as it does to others. So, can you guys hear me? I just checked back over and I see someone saying they're having issues with audio. Okay. Hey, I'm sorry, Romy. I will double check the audio whenever I upload it, but it seems other people can hear me, so I will upload the video and hopefully you can get it there. But let's see. All right. So those barren plateaus that we get from the high dimensional space, you have to be very sensitive with VQE on the types of optimizers that you're using, and because you'll end up with a gradient that's so high dimensional that it's practically flat. Now, another very interesting thing is SKQD. SKQD is a Krylov space variant, and it kind of uses a kernel trick here where instead of just sampling the matrix or sampling the states, it puts it into a Krylov subspace before doing the sampling, which is supposed to mathematically guarantee convergence under certain assumptions. It scales better to some larger lattices. I'm still working on completely getting my head around the math on that, but it's still very interesting by adding this Krylov quantum diagonalization with the sampling methodology that is discovered with sample-based quantum diagonalization. That's SQD. I'm working with applying this to finding stable mathematical knot topologies. Yeah, I know my nerd is showing, but it's I'm really intrigued to find about all the different ways that we can use this to approach these combinatorics and optimization problems that have just been, so far beyond what we're capable of with these classical methods. I've talked about that you don't have to go very far until you achieve a state space that's impossible for any classical computer to be able to investigate. And these methods like SQD and SKQD are really offering some options that, while they're not fully quantum and there are aspects of this that we're still classically optimizing, we're vastly expanding the space that we can actually search by using these quantum circuits. All right, guys, do we have any questions? That's fair, Romy. Um, that's fair. And I didn't know exactly who's going to be attending this event, but at the same time, don't I feel overwhelmed all the time with quantum computing. It's a massive space that combines linear algebra and physics and computer science. Um, all the time I read a paper and I have to slow down, understand what's going on there, and investigate some mathematical method I haven't seen before. That's the normal space, but I'm hoping this is just an awareness of these different methods existing out there as you dive into quantum computing. All right, guys. Thank you so much for coming out. Let's see. Tomorrow we're gonna have our dive into quantum algorithms in the morning. We'll be talking about things like Grover's algorithm and Shor's algorithm, these fundamental algorithms that have these exponential speedups over the best possible classical algorithm, and that's going to lay the groundwork for us moving into the utility scale quantum algorithms on Tuesday. Additionally, tomorrow we're going to dive into optimization hardware challenges on how to specifically format your circuit to meet the demands of what we can fit on hardware. And the big thing I have is that on Monday at noon is we have a guest speaker coming from IBM, Sagarika Mukesh, and her background seems really interesting. Everything from the effects of electromagnetic radiation on biological tissues, and now she's working with the development of the actual hardware and stuff at IBM. So it sounds like she's been able to have her finger in a lot of pies. I'm really interested to see what she's bringing. So please, 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 if you can, make it out for that event. But if nothing else, I'll see you all tomorrow, and I'll be keeping my ear on Discord for the rest of the day if you guys have any questions. All right, guys. Thank you. Bye.